Hello everyone, we are from group 13 and in this time we will present our experiment about distribution of solute between two immiscible solvents. The purpose of this experiment is to determine the value of the equilibrium constant of a solute between two immiscible solvents and determine the degree of dissociation of the solute in the solvent.
The next slide is a theory. According to the Nernst distribution law, when two solvents that do not mix with each other are added solute which can dissolve in both solvents, division will occur solubility. This law only applies if the solute does not experience dissociation or association and for the same components. The two solvents are generally organic solvent and water solvent. In practice, the solute will distribute itself into the solvent was stirred and allowed to spirit. On circumstance equilibrium, the ratio of the solute concentration in the two solvent constant is a constant at a constant temperature. This is called distribution constant or distribution coefficient. The distribution coefficient is expressed by various formulas as follows: K is C1 per C2. If the value of K is large, the solute will quantitatively tend to be distributed more in organic solvent. If the K value is small, the solute will tend to be distributed more quantitatively slightly into organic solvent. As you can see, here's a formula of the equilibrium constant, which means X is log C water, Y-axis is log C organic, slope, which means degree of dissociation or N, intercept is log N per K, coefficient of distribution is a K. And the next is extraction. Extraction is a technique of separating this solvent chemical substance in water by transferring the chemical to a nonpolar phase. Of extraction generally use water and nonpolar solvent because the two types of solvent cannot mix with each other because they are not different polarity. The difference in polarity can separate different chemical wanted. With this extraction method can also be used for determine the coefficient of distribution of a solute in both type solvent.
Tools that we used are Erlenmeyer flask, stative, burette and clamp, Becker glass, volumetric flask, separation funnel, measuring cylinder, watch glass and spatula, filler, and volumetric pipette. And for the materials are acetic acid, diethyl ether, sodium hydroxide, oxalic acid, aqueous, and phenolphthalein indicator. The first procedure is standardize the sodium hydroxide solution with 0.2 N oxalic acid solution. The steps are: make 0.1 N sodium hydroxide solution by dissolving 4 grams of sodium hydroxide in 1000 milliliters of water. Then, make a 0.2 N oxalic acid solution by dissolving 1.26 grams of oxalic acid in 100 milliliters of water. Take 10 ml of oxalic acid solution to the Erlenmeyer flask, add phenolphthalein indicator, and titrate with sodium hydroxide solution until the color changes to pink. Record the volume of sodium hydroxide used in the titration and repeat the step 2 times. The second procedure are to determine the distribution of acetic acid in two immiscible solvents. The steps are: make a solution of acetic acid with a concentration 0.04, 0.08, 0.12, 0.16, and 0.2 N. Take 50 ml of acetic acid and diethyl ether in the separatory funnel, shake the solution until equilibrium occurs. Take the bottom layer that is warm and titrate solution with sodium hydroxide which has been standardized. Repeat this step for each concentration of acetic acid. From our experiment, this is the data that we got. And now is about calculation. First, we must calculate the theoretical mass of sodium hydroxide and oxalic acid. We also have to calculate the average volume of sodium hydroxide, with the value is 20.9 milliliters. Then, calculate the concentration of sodium hydroxide and oxalic acid based on the experiment. The concentration of oxalic acid is 0.20016 and the sodium hydroxide is 0.0957. This is a dilution table of acetic acid to make 5 concentration variations. To determine the distribution of acetic acid in two immiscible solvents, we must to know the concentration of acetic acid in water and diethyl ether. First, we have to calculate the initial concentration of acetic acid before extraction, and after extraction, we got the concentration of acetic acid in the water because we titrate the bottom layer, which is water. And this is the table concentration of acetic acid before and after extraction. After that, we have to calculate the concentration of acetic acid in the diethyl ether after the extraction. To make the curve, we have to plot between log's concentration in the water and log's concentration in the diethyl ether. And this is the curve that we got. From the equation, we know the value of degree of dissociation is 1.6295, that is equal to the slope. And based on the calculation, the value of distribution coefficient is 1.03075.
Welcome to the discussion section, and first let's talk about solvents and solute. Now in this practicum we use two immiscible solvents, which is diethyl ether, a very non-polar, and water, a very polar solvent. Okay, so when these two mix together, they will form a surface that separates them. Why? Because there are a big difference in terms of polarity. So about the solute, here we use acetic acid, which is a semipolar compound that if we mix into the immiscible solvents, we will find that it will be distributed on the very nonpolar solvent and very polar solvent. And now let's talk about the titron standardization. Why do we standardize the titron? It's because the sodium hydroxide, which is the titron, is not stable due to its characteristic of hygroscopic. So we use primary standard, which is oxalic acid, to standardize the sodium hydroxide. And for the main part, the concentration is measured in acetic acid water solution to ensure all of the acetic acid reacts with the water soluble titron, which is, we talked earlier, sodium hydroxide. Volume of the solution is also measured, but here comes the problem. The acetic acid water solution have a different volume before and after extraction. This might be caused by a few water that is partially dissolved in the ethyl ether. So let's talk about the plotting. In the plotting, we have the regression line, and if we substitute it for the equation in the screen, we have the degree of dissociation valued at 1.6295, which is not same to the theoretical, which is 2. Why? Why the theoretical is 2? It is because when acetic acid is in the ether, the acetic acid bonds one another. When it is on the water, the acetic acid bonds with the water. So there are two parts here, 2 parts on water and 1 part on the ether, ethyl ether. Okay, so that is why it is 2. Now, why it is not 2? There might be a chance that not all of the acetic acid in the water bonds with the water, and not all of the acetic acid in the ethyl ether is in bond with one another. Okay, that is why. Now, let's talk about coefficient of distribution, which is 1.0309. It is more than 1, so we can say it. We can say that we can find dissolved acetic acid more in the water. And about the error and solution, volatility of the ethyl ether is one of them. So we can solve this by using the right separatory funnel, the right size of separatory funnel, and not pouring the ethyl ether or any liquid containing long before titration. And the second is water that partially dissolved in the ethyl ether while extracting. So we can solve this by waiting for the system to be well separated before we separate the water. To summarize, in a system of dissolved solute into immiscible liquid, the degree of coefficient and coefficient of distribution can be determined by mixing a variety of acetic acid water concentration with the ethyl ether, and then determining the acetic acid concentration in water by titration. The degree of dissociation and coefficient of distribution is obtained by plotting of log C in the ethyl ether as y-axis and log C in water as x-axis. From the calculations, we can find the degree of dissociation valued at 1.6295 and coefficient of distribution at 1.03075. And here's our reference. Thank you for watching.